Okay, hi everyone. So now we go into our lab number 2. I'll share the screen again. Lab number 2. This is going to be our first write-up lab, like I showed. Have a cover page and purpose, equipment. And when you're putting equipment, put the equipment that is used in the simulations. So don't just say, for example, equipment, astronomy mind tap, but put the equipment that are used there inside of the simulations. And then the procedure. So let's go into it right there. Okay, so let's go to my courses. Okay, lab 2. So you see again, there's 12 activities, 12 things for you to do and record. And when you're writing the purpose, you will gather all of the purposes of all of them. So it will tell you here a little introduction. So in each one, they will give you a purpose. So even though there are 4 major sections, you will unite all those 4 into, let's say, 4 sentences or so. So all of it has to do with the properties of light and its interaction with matter. So introduction. So the properties of light and its interaction with matter. Much of what we know about the universe beyond the Earth is due to our analysis of light and our understanding of how light interacts with matter. So light is very important, especially in astronomy, because that's the only way we know how to discover things in the universe, through the electromagnetic spectrum, through light. So they give you a little introduction to light. And then you can see that they give you the learning objectives of the whole 4 major sections. Describe the basic properties of electromagnetic waves. Describe what a black body is and why it is important. Use Wien's law to calculate the temperature of a hot object based upon the light received from it. And then describe the basic constituents of matter and how they arrange to form atoms. So now let's go back to that section. Then let's go to the second one, light waves. So light is an electromagnetic wave that can travel and carry energy through matter or empty space. So light is unique because it doesn't need, let's say, air to travel through, unlike sound waves. So that's very, very important. Light can travel through vacuum, through empty space. And without that, if it wasn't true, we wouldn't have life, we wouldn't see the stars, we wouldn't get energy from the sun. Nothing would exist, literally, if light didn't travel through vacuum. So it says, because of this behavior, we will concentrate on understanding and describing the wave properties of light, or electromagnetic radiation. The official word for light is electromagnetic radiation. Unlike mechanical waves, electromagnetic waves do not require a medium for propagation, you see? So they don't require air or anything like that. Instead, they are fluctuations in the electric and magnetic fields that can travel through either matter or empty space. So here we illustrate a periodic electromagnetic wave. The electric field is shown in red and the magnetic field is shown in purple. So you see the electric field is up and down like this. And another thing that they didn't mention is that electromagnetic waves are transverse waves. So if the wave is traveling to the right, the electric field is propagating up and down, perpendicular to the direction of the travel of the wave. That's called transverse wave. The electric field is up and down, and the direction of propagation is to the right. And then now they're going to show the magnetic field. You see? And then the magnetic field is side to side, which is still makes it perpendicular to the direction of travel. Think of this, think of this side to side as coming out of the screen. This is coming out of the screen. That part is going into the screen of the computer, you see? Coming out of the screen, going into the screen. So then that makes it, the magnetic field is perpendicular to the direction of travel. And not only that, the magnetic field also is perpendicular to the electric field, you see? You see that? The electric field is up and down, and then the magnetic field is coming out of the screen into the screen, out of the screen into the screen. So then that's how light propagates. And light, what we call light, is only one small sliver of the electromagnetic spectrum. That's visible light. But other than that, the electromagnetic spectrum contains a lot of different kinds of lights, you know, other than the visible light. So that's the next thing they're going to talk about. Oh, they're going to talk a little bit about wavelength of the wave. So it says here, wavelength and frequency are two complementary ways of describing an electromagnetic wave. They are related to each other, and the speed of light by the equation C is frequency times lambda. Lambda is the Greek symbol. So if you're going to type this in your computer, you have to type it as, change the font to symbol, and then press the letter L. And then that will type for you the Greek letter equivalent to L, and then that's lambda. So wavelength is measured, measured usually in like meters, and it would be the distance from crest to crest, or from trough to trough. See, crest is the peak of the wave here, and then the trough is the bottom peak of the wave. So the distance from one crest to another crest, or one trough to another trough, that's the wavelength. Now the frequency is how many cycles the wave is making per second. And that's usually measured in hertz. So you see here, wavelength is usually denoted by lambda, the lowercase Greek letter lambda, right? Frequency is denoted by F, or sometimes the Greek letter nu. But usually we write F for the frequency. It's more common. So it says any collection of electromagnetic waves is called the spectrum. The entire collection, often called the electromagnetic spectrum, is generally divided into 7 regions. So these are all the waves that we give them names, but they're essentially the same thing as visible light. It's just that their wavelengths are different. So radio waves is part of the electromagnetic spectrum. Let me make this a little larger. Microwave is what we use to cook our food, right? And also there's other things that we use microwaves for. So they are also part of the electromagnetic spectrum, then infrared, then visible light. So that's what we usually call just light, you know. That's the small sliver of frequencies that are called visible light. Then after visible light comes ultraviolet. That's what gives you a tan. If you stay in the sun too long, it gives you a burn. Ultraviolet. And then X-rays is what the doctors use to X-ray you. And then finally gamma rays. So visible light is a form of electromagnetic radiation, but constitutes only a small portion of the electromagnetic spectrum. The parts of the spectrum differ only by wavelength, or equivalently by frequency. All forms of electromagnetic spectrum traveling through vacuum obey the equation lambda F is C, and then C is the speed of light in vacuum. It's the symbol for the speed of light. And C is equal to 3 × 10⁸ meters per second. So So the electromagnetic spectrum is divided into regions. The wavelengths are seen to range from radio. So radio waves are the region of the electromagnetic spectrum that are the largest in wavelength. You see, this is depicting that their waves are huge, especially AM waves. AM waves are the largest. That's why you can hear it in mountain ranges. And then FM waves are shorter. So AM waves have maybe wavelengths of 100 kilometers to 10 kilometers. That's AM. FM waves have like wavelengths of 110 meter. So FM is more this region, and then AM is that. So FM can be better heard in tunnels and small spaces like parking lots, whereas AM wouldn't work there. But if you're driving through a mountain range, FM wouldn't work. You cannot travel across the mountains, over the mountains peaks. You can't travel FM. And then when you get to microwave, you're getting to a smaller region than the radio spectrum, smaller, and their wavelengths are about 10 centimeters, 1 centimeter. And the reason they're able to cook food is that their wavelength, which is around 1 centimeter, happens to be about the same size. The wavelength happens to be the same length as the molecules in the food, the water molecules. So then they can resonate with those water molecules, and that's why they can cook, they can warm up a soup or something, So primarily they help warm up things that have water in them, and they can resonate with water. So let's say if you have even a piece of meat, but the meat has also some water in there, some humidity and some water. So then that's how it cooks up the food. Soups, any kinds of foods like that, coffee or whatever you're using to warm it up. So then you have here smaller than the infrared. These infrareds have wavelengths of 100 micrometer or 10 micrometer, or maybe even, I think that's about maybe 1 micrometer, from 100 to 1 micrometer. That's the whole infrared region. And infrareds are known to be like the heat that our bodies give off. So if you want to see people in the dark, you would wear infrared glasses, and you can see in the dark that way because our bodies radiate in the infrared. Then comes the visible spectrum, which is red, orange, blue. So red is the largest wavelength of the visible spectrum, the largest wavelength, which is about, red is about 700 nanometers. So you see, that makes sense. This is 1,000 nanometers is sort of the end of the infrared, right? 1,000 nanometers. Then if you go a little bit smaller, then you get to red. Red is 700 nanometers. Then when you get to blue, blue is 400 nanometers. So red 700, blue 400 nanometers. Then once you get to about 100 nanometer, that's the end of the visible spectrum. Then it ends. Now ultraviolet begins. So these ones have smaller wavelength than violet. Okay, and they have more energy, right? So they're more energetic. They can give burns to you. And of course, X-rays is even smaller wavelength than that. X-rays, you're talking about 1 nanometer, whereas ultraviolet, you're doing 100 nanometers. So ultraviolet ranges from 100 nanometers to 10, and then X-ray would go all the way from 10 nanometers to around 1/100th of a nanometer. 10 to the minus 2 is 1/100th. And then 1/100th of a nanometer all the way to 1/1,000,000th of a nanometer, then that would be gamma rays. Those are the most dangerous. Gamma rays are given off by radioactive elements, and gamma ray technology can be used as a form of therapy to burn off cancer tumors. So it is used actually in the medical world as, but it's got to be very controlled and very, so you have to target the tumor because it can kill other normal cells too. So, okay, now this gives you the whole range of the radio spectrum around 10 centimeters. In nanometers is 10 to the 8 nanometers, and then the frequency is this. So what's going to happen as you go from radio waves down to gamma rays, the wavelength is decreasing, you see. And then visible is 700 to 400 nanometers, you see, right there. So as you're going down, you are decreasing. And then these are measured in centimeters, the same numbers, but changed to centimeters. But now what's happening to the frequency as you're going down? The opposite is happening to the frequency. The frequency is increasing. So radio wave would have like 3 billion hertz, right? 10 to the 9th is a billion. So 3 billion hertz. When you go to microwave, it's going to go from 3 billion to 3 trillion. And then infrared, 3 trillion to 400 trillion. And then it's going to keep increasing. By the time you get to gamma rays, 3 times 10 to the 19 hertz. So that's what makes gamma rays dangerous, because they have short wavelength, very, very short wavelength, but very, very high frequency. And if their frequency is high, they're energetic, they're a lot more energetic. They go up and down a lot more times per second. Okay, so I believe this is the first exercise right here. Oh, basically it's just one where you answer. Again, this one, since there is 4, you don't have to take a picture of each one. Just take a picture of the very last score that you did. Mechanical waves are different. Like, I'm just gonna just randomly answer them without looking at, so then try another version. It gives you 2 chances. Oh, I happen to guess correctly. I'm not even looking at them. So now next. Okay, so then you go to question 3. Okay, so then this is one where you do the ranking. So I'm just doing random. Okay, so wait, submit answer. Oh, it's the same thing. It's forcing me to do it again. Oh, I think this was a different one. I'm not even reading the questions. So, okay, so then you could take a picture of this right here, the snapshot of that. Submit for grading. So question 1, 2, 3, 4, and then you submit. Okay, then we go to, I think there's no more arrows here. So that was the first one. And let's go back to the other one. Okay, so now we go to blackbody radiation. So Wien's law is the relationship between the temperature of a black body and the wavelength at which the most energy is emitted. The temperature is in kelvins and the wavelength is in angstroms. So Wien's law gives the unique peak wavelength of the Planck distribution for a given temperature. Note that to use this equation, the temperature must be in Kelvin and the wavelength in angstroms. A chart showing blackbody temperatures, their corresponding peak wavelengths, and the region of the electromagnetic spectrum to which they belong can be found below. I guess when I hit below. Oh, hold on. Oh, okay. Basically, it goes down to the bottom. Okay, so what is this one saying? So radio waves are emitted. So for a body that's at 0.03 Kelvin, that means like basically just they're barely hotter than absolute zero. So what it's telling you is that objects that are very cool, very, very cool, they will mainly radiate in the radio spectrum. So when they radiate energy, they only predominantly radiate radio. Objects that are from 0.3 to 30 Kelvin, a little bit warmer, they radiate in the microwave. So remember how I was saying gamma rays are more energetic than radio waves? Well, this kind of corresponds to that. The hotter the object, the more predominantly it will radiate those kind of waves, you see. So what kind of objects are 0.3 to 30 Kelvin in the universe? Those will be cool clouds of gas in the universe, very cold clouds of gas. We call them nebulae. So they will radiate microwave or radio waves. And that's why we create radio telescopes and microwave telescopes to observe very cold objects in the sky. Then the infrared it's a wide range. Any objects from 30 Kelvin all the way to 4100 Kelvin will predominantly radiate in the infrared. Their radiation zone will be dominant in infrared. Well, that includes us. Our bodies are around, what, 37 Celsius? Our human body temperature is 37 Celsius. So that's about 310 Kelvin. So our body is 300 Kelvin. It's at the colder end of this region. So we dominate, our radiation is dominant in the infrared. And so is the radiation of all the things around us, the room that are at room temperature, you know, desks, refrigerators, whatever you have, cars, they're all radiating in the infrared. Okay. Then visible, predominantly objects from 4100 Kelvin to 7300 Kelvin, they will dominate in the visible spectrum. That doesn't mean they won't radiate infrared as well, right? So don't misunderstand that. Objects that are that hot will also radiate a bunch of infrared, some microwave, and a little bit of radio waves. And they will also radiate some ultraviolet, some X-rays, and a little bit of gamma rays. But they will dominate in the visible spectrum, you see. Now, when we get to hotter objects, 7,300 Kelvin to 3 million Kelvin, they will dominate in the ultraviolet, but they will also give out visible, infrared, little bit of microwave, very little bit of radio waves, you see. So that's kind of, think of it like almost like a bell-shaped curve, like that. So whatever your temperature is, you're dominating in the center, but you're also radiating around at wavelengths other than where you're dominating. So then this shows you the formula where if I know the temperature of something, I can plug it in here and it will tell me the wavelength that it's dominating, the angstroms. By the way, if you forgot all these things like units like micrometer, nanometer, angstrom, you can go back here and go back to the first lecture. Where they introduced units. I think, was it here that they introduced that? No, it wasn't that. I do remember seeing it, where they introduced the whole micrometer, nanometer, let's see, maybe under measurements. Okay, yeah, they don't have all of them, but they have the main ones. Centimeter is 10 to the minus 2 meters, 1/100th of a meter. Millimeter, 10 to the minus 3 meter. And nanometer is 10 to the minus 9 meter. An angstrom is 10 to the minus 10 meter. 10 to the minus 10 meter, an angstrom. So 10 to the minus 10 meter. So it's basically one off from here. Okay. Oh, and then a micrometer, one micrometer is 10 to the minus 6 meter. 10 to the minus 6. And that's written like this, the micrometer. Where was that? Oh, it was written earlier. Oh, I think I had jumped that. Oh, let's see here. Blackbody radiation. Yeah, this symbol right here. See, micrometer, micro, right there. That's 10 to the minus 6 meters. 10 to the minus 6 meters. Nano is already given in that first lab. That's 10 to the minus 9 meters. And then here we're being introduced to the angstrom. But I think I must have jumped the blackbody radiation. Hold on. Let's go back. Let's go back to blackbody radiation from the start. So a blackbody emits light at different wavelengths based upon its temperature. A blackbody is an idealized object that radiates energy at all wavelengths. The fraction of total energy that is radiated at any particular wavelength depends only on the temperature of the body. In many instances, a hot object will behave like a black body. Its behavior can be described by a set of radiation laws, the most fundamental of which is the Planck radiation law. So we're being introduced to a new law, Planck radiation law. So Planck radiation law describes how much light is given off by a black body at different wavelengths based upon its temperature. The Planck radiation law relates the amount of electromagnetic radiation emitted at a given wavelength from a black body to the temperature of that body. A graph is shown in the adjacent figures of 3 black bodies. There you go. See, that's showing the bell curve that I was mentioning, like a curve. It goes up and down. So it says, note that the peak of the distribution occurs at unique wavelengths at each temperature. As the temperature increases, this peak occurs at shorter wavelengths. Additionally, notice that the area under the curve increases rapidly with temperature. So let's say we have three objects here it's showing. These are the wavelengths that it's emitting in units of angstroms. And remember, angstrom is 10 to the minus 10 meters. So then this object is the coldest of them. Notice that it's peaking, like the peak wavelength is about, let's say 7,000. Hold on, this is 5,000, 1,000. So this is 7,500 angstroms. So this would be 6,000. This would be 7,000 in the graph. So if I had to guess, this object is peaking around 6,000 angstroms. You see? Now, what is this object peaking at? So it's a little bit hotter, temperature T2. Now, if you draw a line, go down, it's peaking at 5,000, maybe 5,050, 5,100, you know. So notice that as the temperature going up, the wavelength of the peak radiation is going down, you see. And then now as this one, draw a straight line, go down, go down, go down. So it's even less than 5,000. So basically, remember how I said earlier, red has a wavelength of 400 nanometers and blue has a wavelength of 700 nanometers. So this object is the coldest out of the three. No, sorry, it's the hottest out of the three. And it will appear more blue. Ah, damn it! They didn't do this picture good. They didn't do the drawing good. They colored it in just to show you the area, but the color that they chose is off. It's making it look like this object will appear red to the human eye. No, it will appear blue. They should have colored this guy blue. They should have this orange is okay because orange is more energetic than yellow. But this one should have been colored blue. Then if there was something colder than T1, its temperature would go like this, its peak like that, okay? Then that one they could have colored red. The other thing that's happening is the area under the curve is getting larger. So that means this object will not only appear blue, it will appear brighter in the sky. It will appear bright. It's going to emit more energy. And then orange is going to be brighter. Then yellow is going to be brighter. Then the red, which is down here, the area under the curve is the least. So it's going to appear the dimmest. Okay, so okay, this is where I pick up from what I was doing, the Vion's law. So, and this is the law that tells you, okay, given a certain temperature, what is its wavelength? So as the temperature goes up, the wavelength goes down, which is what we saw from that graph. So as T increases, 1 over T decreases. Therefore, Vion's law states that as the temperature increases, the peak of the distribution occurs at lower wavelengths. So what could we do here? Oh, we could change the Blackbody spectrum here. You see? So something like our sun, for example, is 5,800 Kelvin. That's roughly what our temperature of our sun is. And then its peak wavelength is going to be 4,987 angstroms. Or if you want to change it to nanometers, you'll say 498.7 nanometers. 498.7. So that's the peak wavelength of our sun, around that 5,800. Yeah, that's what our sun's blackbody radiation looks like. If there's a hotter star in the sky, then it's going to go like that. Notice how this is decreasing as the temperature goes up. And not only it's decreasing that way, in other words, the graph is going from right to left. The peak is shifting. The peak used to be here. It's going all the way there. So it's moving to the left, but it's also moving up because the object is getting brighter. You see? Okay, so the next exercise is this one here. So it's telling you question one. Oh, basically, you're just going to have to fill this in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you're just going to have to fill this in. I guess there's 14 questions. No, hold on. Question 1, 0 out of 14. Oh, points. Those are points. So using the Planck plotter, or the Planck plotter is this one. And the information above, please follow out the following table. Now, since this is a write-up, this is the first table that you will actually make in your Word document under the data section. So you'll have case 1, 2, 3, 4. Just duplicate this table and make it on your Word document. And then this one, temperature Kelvin. So then here, you're going to find out what the temperature of that star is and what region of the electromagnetic spectrum it radiates in. This is 6,000 angstrom. So they want you to find a star whose peak wavelength is 6,000. And then another one, this time the opposite. They're saying set the temperature to 8,000. What is its peak wavelength? And then do this. What is peak wavelength? So let's say if you want to do this, for example, 6,040, you would just essentially just move this until that 6,040, right? So it's pretty easy. It's not too bad. 6,040. Wait, 6,040. Using the Planck plotter and the information above, this didn't reach up to 6,040. It goes all the way up to, oh, hold on. I got to cool the object down to get to 6,040. Oh, yeah, okay. 6,040 is here. Nice. Okay, you see that? So then you put then whatever answer you got, you put the temperature there, and then you put the electromagnetic spectrum. So now let me just guess, for example. Oh, then for that one, you would take a snapshot of each one. So once you put, let's say, the 6,040. Okay, so then take a snapshot, a nice snapshot of this, and show that the temperature is 4801 and show that the wavelength is 6,040 right there. I mean, it's peaking at 6,040. So you see here, this one right here, this is the peak. In other words, it's the peak relative intensity. Even though that star is still radiating in the other regions, you see, down to 1,500 or 3,000 angstroms, but it's mostly radiating around that region, and specifically at the wavelength 6,040. And then it's also radiating in the longer regions too. That means that star will also radiate infrared waves and a little bit of radio waves, you know. But again, it will dominate in the visible spectrum. It will mainly be a visible star, you see. So then you put the number, let's say 4801, electromagnetic spectrum, it's visible. And then you do the other ones. So take a picture of each one Take a picture of each one. And then for one of the rows, so let's say this one or this one or this one or this one. So any of the 5 rows, show how you're getting that missing variable. Show the calculation. That's pretty much it. There is no error for that because we're not comparing it to anything, right? We're not comparing it to anything. So, so let's see how many snapshots is there. That's going to be 1, 2, 3, 4, 5 snapshots of this. 5 snapshots of that. One of this. Make this table in your document, and then show work for one of the rows. And then after you're done answering all of them, take the snapshot of your score. So let me just fill out random numbers here. I'm just going to do I'm going to get such a bad grade. .2 out of 14. I think this one, yeah, that's it. That's your snapshot right there. It will show all the ones that this one will, it will show the score that you got here. 4.2 out of 14. And it will show this, everything that you filled out, right? Okay, cool. So you've got the snapshots for each one and then one whole snapshot. Then next, you don't need this one then. Okay, so you don't need that one. Okay, so now stars as black bodies. Because stars behave approximately like black bodies, we can use Planck's law and Wien's law to determine their surface temperatures using the light that we receive from them. So these laws are very significant in determining the temperatures of stars. So it says here, they gave the blackbody spectrum of 3 stars, Antares, Sun, and then Spica. Intensity normalized. Oh, so what they're doing in this one is even though this is supposed to be higher up and the sun's supposed to be lower down, and Antares is supposed to be even lower. In other words, it shouldn't be as bright as the sun, but they're normalizing it so that they're all at 1. And then they're just focusing on the fact that their peaks are different in this graph. So it's okay. The coloring is also okay. This is going to look blue or violet. So that's the star called Spica. Its temperature is 23,000 Kelvin. The sun's temperature, 5,800 Kelvin. Antares is a cold star. So it will peak in the red region. So this graph is better done. And it is normalized so that all their peaks are at 1. So for convenience in plotting, the intensities of the triggers have been normalized so that each has a value of 1 at the peak. In reality, the size of each curve should increase greatly as the star's surface temperature increases. But it would be difficult to see all 3 curves on a single plot if they were shown with the correct intensities. So that's why they're normalizing it. Oh, okay. So it looks like this is the same thing. The same plot, the plotter. I like this one. You can just find any combination, you know. Okay, now stellar blackbody exercise. So they gave you the region of the spectrum too. Let's see what we're gonna do here. Start. Okay, I guess it's something similar, but this time they actually gave it star names. Procyon, Sun, Capella, Aldebaran, Fomalhaut. So they're giving us the temperature of that star. They're giving us the temperature of that star. So these are actual stars in the sky. And they're having us calculate find out their max, lambda max. So in units of angstroms, you see the symbol for angstrom is an A with a little circle on the top. That's almost like the Swedish letters. Swedish or Norwegian, they have letters where you put a circle on the top. Maybe that's where the name angstrom, it might be that angstrom is actually a Swedish name. What? Let me Google that. Where did the name angstrom come from? What did I say? Nice. I'm so good. There you go. The visible light as wavelength. The unit is named after 19th century Swedish physicist Anders Engström. And you see their names always have these letters sometimes. And I don't know, maybe you're supposed to pronounce it better, differently if it doesn't have that circle versus having that circle. Maybe angstrom, you're supposed to say, if it has the circle. Angstrom versus angstrom. So yeah, that's where that little funny circle comes from. Can you type that in your report? Yeah, you could probably type that in right on the top with the little circle. Okay, so now where were we? So again, you're going to have snapshots here. 1, 2, 3, 4, 5 snapshots from using those graphs right here. Right? 5 snapshots of these. And then make another table, right? And then fill in star, this electromagnetic spectrum. And then once you get all the answers, then fill it in with your data. For one of the rows, show how you're getting, so one of them, show how you're getting this lambda, right? So show how you're getting that lambda. So then again, we can do, I can put in, but this one I don't really need to put in fake answers because we know what's going to happen at the end. After we're done, they're just going to give you the score and then you take a snapshot of that. Oh, this one kind of tries to help you by saying, oh, okay, once you find the wavelength here, you can compare it to this and in nanometers, and you can see where it falls in this range. So let me just show you on the whiteboard how to convert from an angstrom to a nanometer. They're very close. If something is 6,000 angstroms, if something is 6,000 angstroms, you could say 10 angstroms is 1 nanometer. Because the nanometer, 1 nanometer is 10 to the minus 9 meters. 1 angstrom with the little circle is 10 to the minus 10 meters. So the nanometer is bigger by 10 times, 10-fold. So it takes 10 angstroms to fit into 1 nanometer. So then that's going to give you 600 nanometer. So you just basically take the decimal one place to the left, and that's how you convert from angstrom to nanometer. If you wanted to go the opposite direction, you multiply the nanometer by 10 to get back to the angstrom. That's it. So Okay, so stop. Okay, so let's see. Are we done with this section? Yeah, it looks like we are done. Yeah, nothing else there. They should have made a way for us to go back without having to go all the way. It seems like every time you have to go back to this, back to that, and back. Back to this. So I believe we did all of that and all of these. So now structure of matter. Oh, okay. Now they're kind of going through the whole periodic table and how, so, well, why does it keep skipping? Wait, 23C, 23B. Oh, okay, there you go. It starts from here. So I have to watch here. Oh, you know why? Because I've already watched this. I've already seen these. So it's taking me to the page maybe where I left off or something. So, okay, so building blocks. So it's telling you the charge of the symbol for the electron, the charge of the electron, the mass of the electron. The mass of the proton is a lot larger than the mass of the electron. And then the neutron's mass is approximately the same as the protons. Okay, then it's telling you about atoms, that the proton and the neutron are inside of the nucleus. And then the electron goes around the nucleus in shells. So the charge here is negative, this is positive. Of course, this is not drawn to scale because the nucleus is so small, very small compared to the size of the atom. But they're just blowing it up so you can see it. Oh, nothing else on the bottom. Okay, next page. So the number of protons or atomic number. So the atomic number is known as the number of protons, determines the element. The number of neutrons determines the isotope, you see. So the atom is known by its number of protons it has. So it's hydrogen, you see, and then helium has 2 protons. Now the natural helium will have 2 protons, 2 neutrons, but an isotope of helium will have maybe more or less neutrons. Same thing with hydrogen. You can have a hydrogen isotope that has an extra neutron in there. So those are called isotopes. So it says here the total number of protons and neutrons is called the atomic mass number. This lab has a lot of concepts in there, all just meshed into one. So we have here hydrogen, which is the regular hydrogen, deuterium, which is proton and an extra neutron stuck in there, and then 1 electron. And then this is proton and 2 neutrons, tritium. So they're isotopes of hydrogen. And of course, these guys are going to be heavier, right? Because the neutron's mass is about the same as the proton's mass. So this is probably going to be twice as heavy as this, or about twice as heavy. And this guy is going to be about 3 times heavier than the regular hydrogen. So now it says ionization occurs when the number of electrons changes from that of a neutral atom, resulting in an ionized atom, or more simply, an ion. The addition of electrons makes the ion negatively charged. So if I add more electrons to it into the valence shell, the outside shell, then the atom is going to be negatively charged. If I take away the outside electrons, then it's going to be positively charged. So a neutral atom has the same number of protons and electrons. but an atom may gain or lose an electron in a process called ionization. If electrons are gained, the ion is negatively charged. If electrons are lost, the ion is positively charged. So the sodium is 11 protons and 11 electrons. You see, then that's neutral. Okay, now here what happened is, this is known as sodium +1. What happened? The last electron was yanked out. This is how you make actually molecules like sodium chloride, which is regular table salt. Sodium likes sharing its outer electron, and it binds with chlorine. So it gives an extra electron to the chlorine, and then they bind together to form salt. So that would be an ionized sodium, 11 protons, 10 electrons. So since it has less electrons than protons, it's positively charged. Okay. The arrangement of the electrons in the atom shells determines the atom's chemical properties. The first 3 rows of the periodic table are shown. So hydrogen, helium has 2 protons. So these are the atomic numbers: 2 protons. Lithium, 3 protons. Beryllium, 4 protons. Boron, carbon, nitrogen, oxygen, fluorine, neon, and then sodium, magnesium. So so the first shell can only hold 2 electrons, the second 8, and the third 18. So these are the rules for how you can place the electrons in their correct shells. First, you have to complete the first 2 electrons, and then you can place 8 more, and then the third one can fit 18. So there are more shells beyond these 3. However, because of complex quantum mechanical interactions, the order of filling quickly becomes complicated after the first 8 electrons enter the third shell. So the electrons of an atom are found in distinct shells outside the nucleus. So right here, they're showing you how many overall shells. So this is the 2 electrons in the first shell. And then 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons in the second shell. And then 8 electrons max. And then the third shell is 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Then I think you go to the fourth, then back to the third. There's something like that in chemistry, where you go fill out the fourth shell first, then you come back and fill the third shell up to a maximum of 18. You can fill the shell 3 with 18 electrons. But right here, they're just showing you before it starts getting tricky. This is the first, these are the first 18 electrons. Let's see, 2 plus 10 plus 8, 18 electrons that you can fill in that order. Okay, so then let's go to the next one. So atomic notation quickly allows one to see an atom's element, isotope, and state of ionization. So this one is telling you what? This is 6 protons. That's atomic number. 14 is the atomic weight. So if you subtract 14 minus 6, you get 8. 8 neutrons. See, this has 8 neutrons. So 6 protons, 8 neutrons. The combined mass, 14. And one of the electrons has been yanked away from the valence shell. So the +1 is the net charge of that atom. It's ionized. So the carbon has lost 1 valence electron. So atom builder, and I believe this is just a practice one, but then the first atom building exercise is this one. So then start. Okay, now another table to make in your report. another table. And then what are you supposed to do? H110 negative 1. You're supposed to say how many protons it has, how many neutrons, number of electrons in the first shell, number of electrons in the second shell, number of electrons in the third shell. Well, hydrogen isn't going to have much. So a bunch of them are just going to be 0. Magnesium, okay, then you're going to have a lot of the other stuff. I'm not sure what the second row is for. Maybe you're supposed to type that in yourself. So let's see here. Let me see. So like beryllium, mass number 7, charge -3. Okay, yeah, this one you can kind of practice using this. Let's say nitrogen, let's say the charge was -2. So you can say if the mass number is 12, nitrogen has atomic number 7. Mass number is, you can change it here, 13. So then mass number would be 13. Okay. Okay, so the mass number would be 13. Charge would be -2. And then the electrons would be I like that. So we need, if it's -2, that means it has 2 more electrons, right? So it's got 7 protons, 6 neutrons. So 7 protons. Electrons is neutrons is going to be 6. Okay, then electrons I need, if it's 7 protons, I need 9 electrons, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And like if you try to put one more, I don't think it should allow it. Level is full. Yeah. So you could go 10 right there. So then how many do I need? Protons 2. Protons 2. No, sorry. Protons I have 7. And if it has -2, that means I should have 9 electrons. So let me take one of the electrons away. Remove an electron. There you go. Score. Okay, so for example, this is the one you could take a picture of for the second row. It's like you're making your own atom. So then here would be nitrogen. It'd be this symbol right here, you see, in the table, N713. So you would take a picture of this, and then you would just fill this in your table. right? And then fill it in and then press enter, submit answer. And then the whole score will show again. So you would basically have how many snapshots here? For each row, 1, 2, 3, you would have a snapshot of this showing that you did it good. So then you have 1, 3 of these. Then you have a snapshot way at the end when it shows you how many of these are correct when you submit the answer. So you have 4 snapshots right there. And then in your table, in your write-up, you type this table and fill in all the rows, and that's it, basically. Okay, so let's go to the next one. Nothing, no work to show for there because they're not based on any calculations. So I think we're done for that one. Okay, I think we're done for that one. One more left. One more left. And that's the light and atoms. Again, let's make sure I start from the first page. Okay. Yes, that is the first page. So the energy of an electron is constrained by the energy shell it is in. The total arrangements of all of the atoms' electrons is called the atomic state. If one or more of the electrons are in a higher shell than normal, then the atom is in an excited state. Otherwise, the atom is in its ground state. You see, so if something happens and bumps the electron up, then it's an excited atom. It's an excited state. So the energy of an atomic electron corresponds to the shell in which it is found. If all of an atom's electrons are in the lowest possible energy shells, the atom is said to be in its ground state. If one or more of an atom's electrons are not in the lowest shell, then the atom is said to be in the excited state. So after some small amount of time, the atom will de-excite as the electron spontaneously jumps to a lower shell. So the de-exciting means it jumps down and emits a photon of light. For an electron to change energy levels, it must absorb or emit energy. When the electron relocates to the lower shell, it has to get rid of the difference in energy. Thus, the atom emits electromagnetic radiation, having an energy of E gamma equal to the difference between the energies E initial, E final of the initial and final states. The equation stating this relationship is shown on the screen. Just as the electrons can only have specific energies corresponding to the shells that they occupy, the radiation emitted when an atom makes a transition between these shells also has only specific energies. Excitation. An electron will only change energy shells if it can absorb an amount of energy that matches the energy difference. So, but when the electron absorbs the energy, it jumps up. When the electron jumps down, it emits an energy, right? So it says, how does an electron become excited in the first place? It absorbs enough energy of some sort. For example, by absorbing electromagnetic radiation or kinetic energy from collisions with other atoms. So that's kind of interesting. That's how the electrons get excited in the first place, because they absorb energy either by collisions or by absorbing some electromagnetic radiation. Oh, now let's jump down. I think there's an exercise there. Start. So it says, consider the energy levels for hydrogen in the table shown. So remember, for hydrogen, there's only one electron. So now, if the electron is in the n equals 1 shell, then the electron is in its lowest energy. It's in ground state. its energy is negative 13.6 electron volts. If it's in the second shell, the energy is negative 3.4 electron volts. This is actually higher energy than that, even though it looks like the number is smaller, but it's less of a negative. So less of a negative means its energy is actually higher, right? And this is higher energy than that. And this is higher energy than that. So what would be the energy of a photon emitted when an electron jumps from the n equals 3 to the n equals 2 level? Okay, so for this one, you would type this table, type that table in your Word, and then show work for this, how you're getting this, answer. You would type the question down too. So type the question, what would be the energy of a photon when an electron jumps from energy 3 to 2? So type the question down and then answer that question, show the work for that. So the equation for the energy of a photon is E equals hc over d, where h is known as the Planck's constant. Since we know that for light F is c over lambda, we can rewrite the equation for the energy of a photon as hf. What then is the frequency of the photon from your answer above? So if you know the energy, right? If you know the energy, then you can calculate the frequency by using the Planck's constant right here, h. You see? So for example, let's say your answer here was 2.8 electron volts, let's just say. So let's go to the whiteboard. Let's erase this. Energy equals HF. So let's say your energy was 2.8 electron volts. And what's the Planck's constant given as? 4.1356667 times 10 to the minus 11. 4.135667. 4.1356667 times 10 to the what was it? Minus 15. Electron volts times seconds. That's the units of that's one possible way of writing the units of Planck's constant. They gave you that way of writing it, so it's easier for you. This, it's easier to calculate the frequency. This electron volts is going to cancel with that electron volts. And simply, I'm going to divide both sides by this number. So you would type the work for this. 667 times 10 to the minus 15. And then this is seconds, right? So then you go to the calculator. So you say 2.8 divided by, what was the number? 4.1356667. 4.1356667 times 10 to the power negative 15. 6.77 times 10 to the 14 hertz. So that's your final answer. 6.77. Times 10 to the 14. Now, how did I get hertz from that? Well, there's no units on the top. It's just 1. So then I have 1 over second. But 1 over second could mean cycles per second, It could mean revolutions per second. Which are hertz. A hertz is a cycle per second. In other words, cycles and revolutions are actually not really units. It's just something we can replace one with, one of a cycle or one of a revolution. So when you have a unit of 1 over a second, that's actually units of frequency, 1 over a second. So we can now write this as hertz. Okay. So now let's go back to the, so then that would be the answer that I would put for, so I've got the answer for this, then that would be the answer I got this. So then you would show the work for that too, just like I showed. Show the work for that, show the work for that. And what region of the electromagnetic spectrum does this correspond to? And then the choices are visible or whatever. It should be visible because this is the jump. I believe it should be visible. And then you can compare it to this region. What was the answer we got? I think 10 to the 14, right? Yeah, there you go. Yeah. So if it's between 4.3 and 7.5, then it would be visible. So they're always giving you this chart to compare to. So for that one, once you put all the answers, I believe that's it. So once you fill this answer in, once you fill this answer, once you fill this answer, submit the answer, and then whenever whatever score you have, then that's the snapshot you take. So there's only one snapshot for that one, and then this table, fill this table out in your computer, and then type that question, show work for this. Type this question out, and then show your work for that. And then you can type that question out and then answer it. So since it's a write-up, we're typing the questions as well. The questions that are posed and the answers. And if it has to show work, we're showing the work. Type the question and then type the answer. I think that's it, if I'm not mistaken. I think that's it. Yep, that's it. I believe for this lab, there was a lot of calculations, but there were no errors. There were no things that you're going to compare to. So that's good, but just a lot of topics. But when you're discussing your discussion, you can mention sources of error. Even though necessarily we didn't have a % error, you can say, here are things, as I'm doing this lab, here is things that I might have done wrong. Let's say maybe by using that slider or whatever. Here are things that could potentially affect my results. Rounding or using the slider, or maybe you're guessing something, approximating something. So even just because a lab doesn't have a % errors doesn't mean you don't have a discussion section. You can still discuss potential things that are affecting your results as you are doing them. Okay. I know my explanation took a while, but I wanted to be thorough. So hopefully everyone got that. Okay. Okay, guys, see you.